discuss over the next 2 days about the basics of ADS-CFT.
Thank you, David. Thank you, Julian, for giving me this opportunity to inflict on impressionable young minds my perverse points of view on various fields of physics and relations between them. So I've been asked to give an introduction to applied holographic duality, and I guess it's a little bit tricky in that I have the impression that maybe half of you needed an introduction to half of those words, and half of you need an introduction to the other half of those words, and so I'll try to do a little bit of both. Okay, so yeah, so specifically, my goal is to try to give some meaning to the statement that, this seemingly kind of crazy statement that we can use string theory or ideas from string theory to say something about interesting many-body physics, and just to get this out of the way, the class of systems about which we can maybe say something is ones where there's some kind of strong coupling, which prevents us from using techniques that people have been developing since who knows when, so this is roughly so it's an opportunity in that we can do things that people can't do otherwise, and it's also a nice excuse that who knows, maybe we can use this crazy thing to solve these problems that people haven't been able to solve. For the first lecture, let me restrict our purpose a little bit to say that the goal is to make plausible this idea that holographic duality, or what sometimes people call it ADS-CFT, solves certain strongly coupled quantum field theories in terms of some auxiliary variables, in terms of some auxiliary theory of gravity, which in the regime where these field theories are strongly coupled is simple to use. Okay, and I guess I should say I'm going to try to do this in a way which will, for those of you who don't spend your daily lives thinking about string theory and supersymmetry, I'll say those of us who don't spend our daily lives thinking about supersymmetry and string theory, I'll try to present this in a way which avoids that baggage and which doesn't require any sort of intimate knowledge about ways in which d-branes intersect and things that Calabi-Yau manifolds do. For those of you who do, for whatever reason, spend your time thinking about these things, take it as an opportunity to reflect on what aspects of holographic duality are essential, maybe. So, okay. So having begun to offend the string theorists, let me continue for a little while. So what you need to know about string theory for what I'm about to say is the following. It's a quantum theory of gravity, so that's great. But we don't really understand very much about it. One of the things, we don't actually know how to define the theory in such a way that you could, teach enough to teach a computer to say anything about it, really. But one thing we do know about it is that it has many ground states. So, here's a cartoon of this is one of the axes of very many of the configuration space of string theory. One of which is something like the geometry of space-time, or I guess one infinite dimensional subset of which is the geometry of space-time. And on the vertical axis is something like some kind of energy. Now, I guess I don't really know how to define the vertical axis, but I do know how to define it near critical points. And the statement I want to make is that whatever picture we should draw like this, it has many of these minima. And so each of these minima is something like some kind of possible set of laws of physics, and some of them look a lot like, very excitingly, some of them look a lot like the one that we live in, where there's, something like 3 + 1 large dimensions and gauge theory, and under which there's some chiral matter that's charged, and a very small positive cosmological constant, and a long list of experimental data that people have acquired about our world. And I guess it's fair to say that I don't think anybody, well, I'm sure that nobody has found one that matches all of the things that we know about our world yet. And that's a good goal. Somebody should do that. It's not going to be me. But in fact, most of them look nothing at all like that. They have 10 dimensions or 2 dimensions, or no notion of space-time at all. And so some of them just and some of them have a negative cosmological constant instead of a positive one, which if you don't know yet, it makes a big difference. Well, as we'll see. And okay, so this situation that I just described is, it makes the business of doing string theory a lot more like ordinary science than you might have thought in 1985, in that you have to match the experimental data that you already have, and then see what predictions you can make. It's so crazy, rather than just thinking about it for a little while and scribbling on a piece of paper and writing down the mass of the electron. But from the point of view of trying to use this in the way that we'll describe, of trying to use it to say something about states of matter, it's an enormous virtue, because each of these ground states, at least many of these ground states, at least the ones with negative cosmological constant, describes some possible universality class of critical behavior, some fixed point of the normalization group about which we can perturb, which has some basin of attraction. It describes some class of many body phenomena. And so this abundance, or what many people view as a overabundance of the string landscape, mirrors in a way which we're very far from being able to make precise so far, the landscape of possible many body phenomena. So this map is certainly not in any way known to be one-to-one or onto, or even yeah, okay. Well, so one of our goals is to address the nature of that map. Okay, and so one thing that I'll emphasize in a little bit is that both of these on both sides of this correspondence, there's some notion of tuning, in that when people study condensed matter systems, there's a huge selection effect that if you synthesize some material and you measure the current across it and it does something boring, and then you throw it away. Whereas if you and you do that for a whole bunch of them, you throw a whole lot of them away, and then one of them does something interesting, you keep that one. And so that's so according to this duality, that's dual to the anthropic selection effect that leads to why we live in a vacuum with small positive cosmological constant. Okay, I'm sorry, that was a joke. Okay, so okay. I have to resist saying things like this. I'm being videotaped. Okay. But independent of this joke, this is I think a very important opportunity, at least for those of us who have invested quite a bit of time in thinking about string theory, to make contact between string theory and experiment, not in the way that we might have hoped a while ago, but in nevertheless what can be a very real way, and even without understanding the details of this map between ground states of string theory and with negative cosmological constant and many body systems, this holographic duality can teach us quite a bit. In particular, it offers insight into the structure of quantum field theory in a way which is completely unavailable in other ways. So in particular, let me make a collection of promises which some of which I'll try to keep, and I think other lecturers will do more to keep, in that it allows us to calculate. So suppose that you have a quantum field theory that for some reason or other you're interested in, which has a description of the nature that we're going to describe. So suppose it is described in terms of these auxiliary classical theory of gravity and extra dimensions, then, we're going to have long arguments about whether there is any such field theory of that nature, which has anything to do with any real experience. But forget that for a moment. Let's just suppose that you have one that you're interested in. Then it's a pretty amazing situation, because you can calculate things which are totally uncalculable otherwise, like Green's functions as a function of frequency, momentum, and temperature. and dynamical things like the energy loss of moving probes, potential energies between static external charges, entanglement entropy of subregions. In situations, so not just in the ground state or in equilibrium, but which are by themselves difficult for calculating even simple things using ordinary techniques, such as, so I've already said we're at strong coupling. We can, if we're willing to do a little bit of numerics, we can do things far from equilibrium. Sometimes even if we don't, sometimes we don't even need to do numerics to do that. We can do things in real time, and we can also do things where ordinary techniques fail because of the fermion sign problem. So finite densities of fermions faces different problems than one does in lattice calculations. Okay, so here's my plan. For the rest of this lecture, I'm going to try to give a string theory-free motivation for this duality and introduce the basic dictionary. I guess I have to apologize to those of you who have heard me tell this story before. And then probably starting at 4 p.m., I'll try to illustrate the machinery of this duality in some detail, but not too much detail, hopefully. I'll try to show how the machinery works without grinding your nose in it, to calculate correlation functions in anti-de Sitter space as an illustrative example, and then we'll talk about how to study finite temperature physics using black holes and why that works, and maybe a little bit about transport. And then so my goal in most of this is to satisfy those of you who are coming from having spent time thinking about condensed matter physics or things other than string theory. And then in the third lecture, I'm going to try to give my favorite answer to the question of, well, what system should we try to apply this to, and what should we use this for? And something that I can't stress strongly enough is that in this business, I've said all these wonderful things that this machinery can do, but I think it's important to emphasize that finding the right question to use it for is really the most important part. And an answer to that, which I've been focused on and continue to focus on, is applications to systems with Fermi surfaces. And I'll explain why I think this is a question for which this machinery is suited. And the basic reason is that you may have noticed that a large N gauge theory is maybe not the best starting point for modeling the behavior of electrons in a solid. And so therefore, to learn something about electrons in a solid or any kind of condensed matter system, it's important to find questions where that difference, that microscopic difference, isn't in your face all the time. And so this is one of those questions. Okay, so here are some references that I like. I'm going to follow this review for a little while. Okay, so this is a good point for me to emphasize that you need to ask questions. Otherwise, I'm going to get tired of talking, and I may even stop. Okay, so I think I've already said some pretty provocative and probably wrong things, and I need you to call me on this. All right, so I'm going to stand here like an idiot for 30 seconds and try to provoke you into talking. Yeah, please. It doesn't work?
Is Fermi surface a provocative word?
Is Fermi surface a provocative word? Well, I didn't intend it that way, and actually I think that one's pretty safe because the property of a system that I'm ascribing to it here is something that's measurable. So whether or not a system has this feature, at least, well, okay. Whether it has an electron Fermi surface is something that you can measure by angular resolved photo emission. So you shine light on it, you kick out electrons, you measure as a function of the frequency and the angle of the incoming light and the outgoing electrons where are the cheapest excitations. And if in momentum space the cheapest excitations lie on some locus of some finite dimensional locus in momentum space at zero frequency, that's what I mean by has a Fermi surface.
I guess what I meant is that is there consensus on having a holographic Fermi surface?
Okay, yeah. So no, no, yeah. So exactly how to apply this machinery to that problem, I think, is still there've been some, I think, interesting ideas about this, but I think it's still an open question, which deserves further attention, and I'm voting with my feet on that particular question. Good. More questions?
Oh, John,
Yes, good.
do you think that really all the many vacua that are there are actually boring, and so like lots of materials that we understand, and there's only very few that we don't understand?
Okay. So Julian is asking about my duality between selection effects. Yeah, so you're right. It may not be exactly the same selection effect as throwing away the materials that do things that we're used to. No, in fact, I think most of them are much more different than from things we understand than even we can imagine. Yeah, so I guess this is an important point to emphasize. We don't know anything about the string landscape. Nothing at all. So there are a few ground states of string theory that people know how to construct using supergravity, and like a few little like doohickeys that you can add onto supergravity. But it's totally a lamppost phenomenon. So it's just some little tiny corner where we're able to compute things, where people have constructed vacuum of string theory. And there's this huge uncharted territory at finite coupling and at finite radius of the geometry, or even in situations where there's no geometry at all, which is totally unexplored. So I think it's the boldest of hubris to imagine that we have any idea of what a representative vacuum of string theory is. Okay. So, yes, please.
Is it possible that you know or not that some of these ground states are more likely than others?
Okay, so so this is definitely a provocative question. So the question is about whether some of these ground states are more likely than others. So I think so far I haven't said anything about which of them are like realized in some cosmological situation, or whether they're like universes in which this physics is taking place. So far, I've just said that they exist as critical points of some effective potential, and that latter question of the population of this landscape is even harder, and let's say I'm not prepared to say anything about that. Yeah, so putting a measure on the set of string ground states is a dicey problem. Yeah, but we won't have to think about this. Yeah, so that's one thing that I can safely evade. Okay, so here's the beginning of this discussion. I want to start by saying this totally insane statement that you're all going to believe by the end of tomorrow, and then we'll try to figure out what I mean by it. So the first part of the statement is some ordinary quantum many-body systems are actually quantum theories of gravity in extra dimensions. Okay, and so what I mean by a quantum theory of gravity is a system described by quantum mechanics where the space-time metric is one of the dynamical variables. In general, we don't really know what that is, but I'm telling you that this is a real thing. Systems you consider sort of ordinary prosaic things can be realizations of that. By itself, this isn't so useful because like I said, we don't really know what this is. But the second part of the statement is that sometimes there are even classical theories of gravity, and we really do know what classical theories of gravity are. It's just some simple differential equations with some boundary conditions. Not to take the magic out of it or anything. Okay, and so now I need to explain how this can come about, and to do that, I'm gonna bring to bear two hints from widely different fields of physics, which I'm going to explain in a very heuristic way. So Okay, I'm going to be heuristic. That's a disclaimer. And so the first one comes from the renormalization group, which I think I can assume everybody knows about. I'm going to assume everybody knows something about it. And the other comes from the holographic principle, which I can imagine there's no reason for some of you to know about that. Okay, so first the renormalization group. So a thing that you're all supposed to know is that some time in the last century, people started doing experiments where they studied continuous phase transitions and measuring critical exponents for various observables. So, for example, a ferromagnet near its Curie transition as a function of this reduced deviation from the critical temperature. If you measure the specific heat, it satisfies some power law. If you measure the magnetic susceptibility, it satisfies some other power law. But then some completely different system undergoing some phase transition with the same kind of symmetries and the same number of dimensions. So say water near its liquid gas critical point. If you measure its specific heat, it satisfies the power law. And if you measure its compressibility, it satisfies the power law as a function of this. And the magic is that this number here is the same as this number here. And so that's something that requires some explanation, and that explanation comes from this renormalization group idea, which is to think about the system, which for each of those two cases I just mentioned, you could imagine a lattice description of it where the degrees of freedom sit at some sites of some lattice, which I've drawn here as a square lattice. And imagine imagine I had enough time on my hands to draw a little arrow at each of these corners. Imagine, so there's a specification of the configuration space of the system, which is a little arrow at each of the corners of this graph, and there's some Hamiltonian by which the little arrows interact with each other. Imagine it's a lattice gas description of water, or imagine it's a description of this ferromagnet where there's some interactions between spins on nearby sites. I should have emphasized this. It's important that there's some locality built into this Hamiltonian so that only spins that are close enough to each other talk to each other. And then the idea is group some collection of these spins together and think of the average of those spins as some effective spin for a coarse-grained system, and then reconstruct a Hamiltonian for those coarse-grained spins. The Hamiltonian will take the same kind of form. There'll be some plus some corrections, which will become unimportant, and in this way we construct a flow on the space of Hamiltonians. So because there will be some new value of the coupling constants for the block spins at the next step, and so in this way we have a sequence of theories living on coarser and coarser lattices as we move in this direction, which I think u is the coordinate I'm going to call. No. 1 over u is the coordinate which goes towards the infrared, towards coarser and coarser lattices. And okay, and so this defines a flow in the space of Hamiltonians, which and the existence of fixed points of this flow is the solution to the puzzle about how you could possibly get the same critical exponents in different systems, because the critical exponents are properties of the fixed point, and each fixed point will have some basin of attraction. So very different microscopic theories can flow to the same fixed point, and you'll get the same exponents. Okay, and that fixed point theory is scale invariant in that if you change the resolution again, you get back the original theory. That's what it means for it to be a fixed point. And I guess in any discussion of the renormalization group, at some point, after doing like the 1D Ising model, you realize that these sums that we just talked about, constructing the block spin Hamiltonian, are actually kind of hard to do. And wouldn't it be nice if there were some machine which gave you some differential equations for those renormalized coupling constants? And we'll see that there is sometimes. Okay, so that was the review of the renormalization group, in case you missed it. The property of the renormalization group that I want to bring to your attention is the fact that it's local in scale. And so what I mean by that is that, so what I mean by a quantum field theory is some family of trajectories on the space of Hamiltonians, labeled by, you pick an initial condition, you get some flow in the space of Hamiltonians. And at each point on on each of those trajectories, we can expand the Hamiltonian in some collection of local operators, the operators that can possibly appear in the Hamiltonian. So that's some list of operators O, and so the coefficients there are that's what we mean by coupling constants. There's some functions of U that's what changes along the flow. And the point I wanted to make is just that because of the fact because of the by construction, because the Hamiltonian at scale U is defined by this procedure, which starts from the previous step, it's manifest that the equation governing each of these coupling constants, governing their evolution in scale, that is the beta function, is local in scale. That is, the beta function at some given scale depends only on the couplings at that scale, and not the couplings at some microscopic scale that you've forgotten about long ago. Okay, so that's, and then okay, just this is an opportunity to define some notation. Excuse me. Near a fixed point, this beta function is determined by the scaling dimension of the operator O, which is defined in this way, by how much do you have to scale the operator. When you scale, by what power of this ratio of scales do you have to rescale the operator. Okay. And good. Okay, so that was the first hint. The second hint.
Can I ask a question?
Yes, please.
Did anybody take this hint?
Yeah.
Did anybody actually suggest that this RG flow could be viewed as an extra dimension?
You mean before ADS-CFT? Did anybody?
Polyakov maybe, but not so explicitly.
Yeah, but I guess Polyakov was thinking of ADS-CFT when he suggested this, or some scale-dependent version of it. Not that I know of yet. That's the best example I know, I would say. Yeah, so I guess a question that someone could ask me is, well, how local is it? Meaning, does this really mean that you can describe the evolution in terms of some system of differential equations in an extra dimension, which looks like a field theory in some extra dimension? And that's definitely not clear from just this information. In fact, that is to say, ADS-CFT works much better than you would expect just based on this. Okay. The second hint comes from thinking about gravity. So far I haven't said anything about gravity. And it's okay. So the first hint was to say, what is the extra dimension? And the second hint is to say, why is it okay that we're relating two theories in different numbers of dimensions? Okay, and so by the holographic principle, I mean the following thing, which is sort of the maybe the most information we have about quantum gravity. It's like maybe the only thing we know about it really, in general, which is that in a gravitating system, in a system with gravity, the maximum entropy that you can fit in some region, which I'll call V, is proportional to the area of that region, the area of the boundary of that region. That's the entropy is dimensionless. The area has dimensions of length to some power. The thing that makes up the dimensions is the Planck length. So that is the length that you can make out of h bar and c and g Newton, in a way which is left as an exercise for the reader. Okay, so what I mean by the maximum entropy here is like the log of the dimension of the Hilbert space. So the number of degrees of freedom. And to get some intuition about what I mean by that, think about an ordinary system like the ones that I was describing a moment ago. Imagine I were instead talking about a quantum system where at each of these points there's some qubit. It's some two-state system which has some two-dimensional Hilbert space. And so when we tensor together the Hilbert spaces of each of those qubits to get the Hilbert space of this big thing, this number grows like the number of sites, or alternatively like the volume. So the whole Hilbert space is 2 to the n dimensional, and so this quantity is n log 2. And so in particular, it grows like the volume of the system in a system which is constructed by tensoring together Hilbert spaces of local degrees of freedom. And so what I'm saying is that a theory of gravity is very different from that. Okay. And in particular, there's less stuff in it. Okay, and so to see why this is believed to be true, let's combine two facts. The first fact is that a black hole has an entropy, which is proportional to the area. It's the area of its horizon in these same Planck units. So this is the Beckett-Steen-Hawking formula for the entropy of a black hole. I guess I'm not going to defend the statement. I guess in Cambridge you don't have to defend the statement, maybe. Okay, and well, I guess maybe I'll say a little bit about it. Okay, so notice this is dimensionless, and I've set h bar and c to 1. So the only thing left with units is this Newton's constant, which has dimensions of length to the d minus 1, where d plus 1 is the number of space-time dimensions. So d is the number of space dimensions. So happily, this is dimensionless. I've also set Boltzmann constant to 1. Okay, and good. Oh, good. So I am going to say a little bit about this. So to see that black holes have an entropy, we can take for granted the fact that they have a temperature. Maybe that's the safer thing to do. Though I guess I will explain a little bit more about that in the second lecture. But in particular, the temperature of the Schwarzschild black hole in flat space has some dependence on the mass of the black hole, which is something like this. And then, well, the mass is the energy over c squared. And so in order to have a consistent accounting of thermodynamics in a system which includes black holes, the first law for change, if I change the energy of the black hole a little bit, throw something in, then in order for the first law to be true, if I do that quasi-statically, then I'd better be able to account for that by the change in entropy of that black hole. And so in particular, it has to be non-zero. And then combining this formula with the expression for the temperature and integrating gives us up to a proportionality constant that the entropy of the black hole is the area. And so this forces us to think about a generalized second law, which allows for the entropy of ordinary stuff, the stuff that you usually think about, and then plus the entropy of black holes. Okay, and then the second fact, which combines with the first to convince us of the inevitability of the holographic principle, is that black holes happen. Is that if you put enough stuff together, it'll form a black hole. So combining these two statements in a gravitating system, the maximum entropy that you could fit into a region of space is the entropy of the biggest black hole that fits. Because if it weren't true, so suppose you had some stuff in some region of volume V, whose the area of whose boundary is A, then and whose entropy was bigger than the entropy of the black hole, the biggest black hole which fits, which is A over 4g Newton, but whose energy was less than the energy of that black hole, then you just throw in all your garbage. Your garbage carries both entropy and energy. So by doing that, you increase the energy. But eventually, if you compact all your trash into this region, eventually it will gravitationally collapse. And do this until you make a black hole. So this is where we're appealing to fact 2. And so by doing that, you end up with a configuration where the entropy is less than the initial entropy. And so then you can just use this to power your planet for forever. Yes?
Regarding the error law,
Mm-hmm.
especially in the previous slide, how general is that?
Good.
Varying the model of gravity.
Yeah, this is a good question. So this formula for the entropy of the black hole assumes Einstein gravity. It assumes it makes some assumption about the action for gravity, and it is true in Einstein gravity. And more generally, the thing that goes here is in a classical theory of gravity is some functional that you can construct from the action, depending on the curvature, which
you can modify that law by adding some other fields, scalar fields. For example, the air doesn't depend on the temperature. Then.
So yeah, this is a big subject. So let me make a statement which is true. If I have a theory of gravity where the action is not just the Einstein-Hilbert term, but rather is some more complicated functional of the curvature, but not yet including other matter fields, then there's a formula due to wall that replaces that goes there instead. And then in the presence of matter fields, there's this interesting question that, we're trying to ascribe some meaning to this quantity. We want to say it's the entropy of the black hole. So, therefore there should be some microscopic accounting of it. It should be, the exponential. It should be the log of some number of states. And so in particular, that number can't vary continuously. So for example, this means that if you have, say, some scalar field in your system, the answer for the thing that goes there can't depend on, some value of the scalar field that you get to pick. So this is this was a puzzle, which is solved by what's called the attractor mechanism, which is that in general, the behavior of the scalar fields near the horizon is something fixed and ends up always being integers in the right way.
Fixed, depending. I mean,
So it's not something that you can vary by boundary conditions. Yeah. So this. Yeah. Okay. I think this is an interesting subject, but I think I should proceed. Yes.
Are you familiar with the ideas of Duality? I think he's contesting this
Duality.
interpretation of black holes. He says that they don't really have a temperature.
So we're disagreeing with this one here.
Yeah,
I'm not familiar with that statement. Really?
yeah. From my understanding, which may be.
I would be eager to learn about that. But I don't know anything about it.
What's the statement?
So the slanderous attribution has been made that Guy de Valle claims that black holes don't have a temperature. Yeah, I mean, you might, in England, the laws are pretty strict. But I can't comment on this. You can tell me about this later. Okay, but I think it's true. I'll tell you why I think it's true next time, and you know why I think it's true. Yeah. Okay, and so the outcome of this line of argumentation is that the maximum entropy that you can fit in some region of space in a theory of gravity is the entropy of the biggest black hole, which goes like the area of that region, not like the volume. And so in particular, a theory of gravity in d+2 dimensions has the same number of degrees of freedom as a local theory in one fewer dimension. Okay, so this is a crazy thing about quantum gravity, and we don't really know how to construct models which realize it from first principles. And only in very special cases, like the ones we're going to talk about, do we actually know how to do this. Okay, so combining these two hints, the conjectured meaning of the bold assertions that I began with is the following. Maybe we can say that gravity in a space with an extra dimension, whose coordinate is the energy scale, so that's the one extra dimension that over which this paucity of degrees of freedom is distributed, could be a quantum field theory. Could be the same as some ordinary quantum system. And to make this a little more precise, let's specialize to a simple case where there's extra symmetry, which is the one where it was first realized. Okay, and so in particular, let's think about a relativistic field theory, because who wants to have to distinguish between time and space? And so, which has the further property that it's scale invariant. So that is to say, we're going to sit at, or actually, sorry, I'm going to even ask for a family of fixed points. So where the beta function for the couplings is just exactly 0, just for argument. And so then it has some scale symmetry under which all of the space-time coordinates scale by a factor of this parameter lambda, and u, which has the dimensions of energy, therefore scales oppositely. Okay, this u is, remember, this RG coordinate, which is, it's like the energy. Okay, and then a space-time that realizes d-dimensional Poincare symmetry, but d is the number of space. Oh, geez, I changed it, didn't I? D is now the number of space-time dimensions. Is Minkowski space, right? So there's this thing is invariant under acting on t and x by SO1 comma d minus 1 rotations, right? So this is special relativity. And then if I demand this symmetry plus the scale invariance acting on this extra coordinate u, the metric that we end up with after a little bit of jiggling is this metric. So it's a bunch of copies of Minkowski space that's sitting right there. And then because these t and x scale like, so t scales like lambda, dt also scales like lambda, dt squared scales like lambda squared. And so I have to stick some power of u here to cancel that, that scaling. And so it has to be u squared. And then we want to have some length in this radial direction also. And so to make it scale invariant, we have to divide by u squared. And so by this simple argument, we've discovered a spacetime which is called n-to de Sitter space. And this parameter L, which appears here, is not fixed by anything. It has dimensions of length. No, it has dimensions of energy. Yes. No, it has, oh, sorry, let's see. What is going on here? It's so confusing. It has dimensions of length or energy. I guess I wanted to have dimensions of length, yeah. Because, no, good. Here, this is obvious. If this is dimensionless, this is a length squared, this had better be a length squared. Good? Everybody agree? Thank you for your patience. So that's called the ADS radius. I should have taken that hint. Yeah. Okay. Sorry. And so it's a bunch of copies of Minkowski space whose size, in the sense that this metric is encoding the distances between points, whose size varies as we move in the u direction. And notice it actually also has a larger symmetry, which is conformal symmetry, which is SOD, 2. And by the way, I guess the thing we just proved that scale invariance plus of a Lorentz invariant fixed point with the description in terms of gravity implies conformal invariance in any number of dimensions. Okay. I'm going to introduce another coordinate, which is better.
There are counterexamples to that, right? In field theory.
Yeah, they don't have a gravity dual, right? Yeah. So right.
Is that really right? You think?
They don't have a simple gravity dual, right? Yeah. Yeah, because you could imagine, for example, I guess you could imagine that there are other fields in the problem which break the symmetry, which I haven't written down. Yeah. So I guess that yeah, maybe I should erase that. Yeah. 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 Right. So this. Okay. The subject of counterexamples to this is an interesting one, which we will not speak about now. Okay, so another coordinate which is useful, which is completely equivalent to the u coordinate, is 1 over the u coordinate, with a power of this ADS radius to make it have the right dimensions, and it's better because you can write the metric all in one thing like this. Right? It's simpler to write, and notice that this z has units of length. So I will. Okay. Okay, so here's a picture of n-to de Sitter space. It's a bunch of copies of Minkowski space whose size varies with this radial coordinate. And my job here is to convince you that this picture is the same as the pictures I was drawing earlier of the renormalization group. So that in the same way, this is describing a single field theory, or rather the history of a single field theory under its renormalization group evolution. And so, it's a sequence of snapshots of the field theory at different energy scales, which is put together in a way, in one picture, in a way where you have fields smoothly propagating on the spacetime in a way which tells us about the dynamics of that theory. Okay, so putting all these things together, our preliminary conjecture for what I meant by those bold assertions is maybe a conformal field theory in d dimensions, so that's this special case where there's scale invariance and conformal invariance was kind of an output. Maybe that's the same as gravity in n-to de Sitter space, right? That's where we are right now. Are you there too? I'm happy to answer questions if you want to talk about it.
No, actually, I was wondering whether your assumptions about locality of the RG flow and the locality of gravity imply that you have to have some sort of mapping between the two, because in gravity beside the locality of the evolution, we also have the problem of the global evolution.
Global constraints in time.
Exactly.
Yes. Yeah, that's a tricky thing. But in fact, certainly the heuristic arguments about locality of the RG is not enough to conclude the strong form of local field theory that we'll end up with. Yes, you should take it as a motivation and not as something precise.
There might be other roads.
Well, historically, certainly that's the case. That this was discovered in a way very different from the one I'm describing. Yeah. But you're right that there are some senses in which a theory of gravity is not a local theory, and in particular, the counting of degrees of freedom is one of those. Right. That constraint that you're talking about is exactly something that's in the Hamiltonian quantization of some metric theory of gravity. That's one of the ways in which it's made explicit that the counting of degrees of freedom is not extensive in the volume. But
It
yeah.
follows from local differential equations, even that statement.
Yes,
The RG could be in the same way, non-local.
yes, that's right. So what I meant by local is really that there's some differential equations which where you don't there's no integrals in the differential equations, at least if you do it right. I guess you could, yeah. Anyway, there's a way to write the equation so that there's no integrals. that's a better statement. Okay. Yes, please.
I had a similar question. I'm not sure if it was directly answered by what you just said, but on the quantum field theory side, you talk about locality, so this I understand. The locality that you were talking about on the quantum field theory side, in the Hamiltonian, etc., how does it exactly translate on the gravitational side? Is it just how to go from one hypersurface to the other?
Yeah, good. This is an important question, actually. So it's totally true that the locality in the radial direction, the locality in the RG space is a consequence of locality in the field theory. So just as I'm not sure if I can give an answer that everybody will be happy with for why this happens, but just think about the block spin procedure. So when you first do the block spin transformation, when you compute the averages over the block spins, the Hamiltonian that you get is not exactly of the same form. Rather, if you start with a system with only nearest neighbor interactions, at the next step in the RG, you get next nearest neighbor interactions, right? And if you keep going, the interactions will spread. And so it's important. Whereas if you started with interactions between everybody, you would always have interactions between everybody, and I think there's no sense in which you could expand and in a way expand the interactions in the separation in a way which allows you to forget about what happened previously in the RG. I guess so. My difficulty in answering this is that if the interactions are not local, we just have no idea how to do the RG procedure. I think is the simplest statement.
I guess in the back of my mind, the question I had was, is the RG procedure in the quantum field theory side somehow not exactly the same, but closely related to hyperbolicity of the Einstein's equation? The fact that you can evolve data from a given initial hypersurface to the next step, but along radial evolution, not along time evolution in that instance.
Yeah, good. This is a good question. No. So in the following sense, the duality that I'm trying to describe to you is an equality of quantum systems. So the statement I'm trying to sell you is the Hilbert space of some quantum field theory and the Hamiltonian on the Hilbert space, which is what tells you how to time evolve it, is the same. Can be described equivalently in terms of some other set of variables, is the same as the Hilbert space of this quantum theory of gravity, and a certain notion of Hamiltonian constructed from that. It's not exactly the Hamiltonian for this usual reason that h equals 0, but there's some issue with the boundary conditions that allows you to have a well-defined Hamiltonian evolution in anti-de Sitter space. And so that time evolution maps to the time evolution in the field theory, and the radial evolution in the RG direction is evolution in this other space direction. So I would say I think my answer is no. Each of them has two notions of evolution, which map to each other. If you ask me exactly how they map to each other, we'll get into all kinds of confusions about coordinate changes and things like this. But the fact that there are two is I'm sticking with. You look unhappy.
Maybe I'll come back to you and ask.
Okay, good. All right. So, but
I have only one more question on that issue. Sorry.
only one.
Would you say that I mean every time that you have some holographic setup and you have something like a radial coordinate that's in RG direction?
Well, okay, in RG direction. Yeah. If you use the indefinite article.
Okay.
Yeah, because I mean, there's of course this. So this
Let me use the definite article.
with this business about coordinate redefinitions is, how to say, there are many possible RGs in a given system, right? You can.
No matter how crazy the interior is, I mean there are.
Well,
Like an electron star, for instance.
I haven't found one where it couldn't be interpreted that way, right? Yeah, I don't know. I mean, I think that's a good default hypothesis that we can always interpret it that way. There are a few interesting. Well, okay. Yeah. Okay. Yes.
What happens if you start from a system of spins, say, with everything interacting, and you can certainly formally define the RG flow, right? But so what do you mean we have no idea and there is no useful distinction of relevant and irrelevant directions?
Well, who do you group? What blocks? So the question. Did people hear the question? Okay. So the question is what goes wrong in the RG if we have interactions between everybody? And my answer is, in the block spin procedure here, we group together nearby spins because they're the ones that interact with each other the most. Whereas if everybody interacted with everybody, we wouldn't gain anything by doing that, right? Because we wouldn't be, the point of it is to group together the ones that are interacting first, right? The ones that the strongest interaction first, and so they form, those interactions will make them form a spin by themselves, and so then, I don't know. Yes, please.
In the block spin example, I can quantify the information that is being erased out in each coarse graining step. What
Yes.
does that correspond to in the gravity side?
That's a good question. So the question is about quantifying how much information is being coarse-grained away in doing this procedure, and whether we can translate that to this picture. And I think that's an open problem. People have made a little progress on this recently, I guess. I don't. Does anybody else want to answer that question?
I think the near horizon geometry, the same, many different gravitational setup can share the common near horizon geometry.
Certainly, yes.
So this should be related.
Yeah, that's the same kind of consequence of universality, right? That a fixed point can be approached from many different ways. Yeah, but quantifying what it is that we're forgetting when we approach the fixed point, I think, is maybe harder. Yeah. Okay. So this, it's really bothering me that this wrong statement. I guess there's a question mark here, but the fact that there's this wrong statement here, I want to fix it. But yes, please go ahead. Go ahead.
Just because, so you in your metric use that you scale the space and time in the same way.
I was making the simplifying assumption that it was a relativistic theory.
Yes. So, but in some quantum critical points, you know that your dynamical exponent is not one.
Right.
What happens in that?
Oh yeah. So that's a good question. So I was focusing on this case for simplicity. Various analogous things have been constructed attempting to generalize it in exactly that way, which maybe I'll say a few words about a little later. Okay, yes?
So just the interpretation of the extra dimension is kind of based on the classical version of ADS IFT.
Yeah. So I'm assuming that there's a useful notion of dimension.
Yeah. So if you had, I mean, is it? So when you have the full quantum theory?
I don't know.
No one knows. Or?
Yeah, no one knows.
Okay.
Yeah, you should figure that out. I should emphasize this. I'm going to focus on the case where the description of the gravity theory is a classical one, where we really know what we're doing. In which case, we can expect some information to flow in the direction of the the field theory. And then, once we understand that well, then we can do it quantum mechanically. It won't be any problem. Okay, so a very important refinement of this wrong statement that's been sitting here in front of you for all this time is that my definition, the very definition of a theory of gravity, is that the metric is fluctuating. And so that means it makes no sense at all to say, this phrase is total nonsense, right? It's been, this nonsense has been staring at you all this time. So to say what I mean by gravity in ADS, I need to emphasize the following point. So Enter de Sitter space is it's a funny space-time because it has a boundary. It has a time-like boundary, and to reach the boundary, you go in the direction u goes to infinity. So u is this coordinate. So you go in the direction where the copies of Minkowski space become really big. So or z goes to 0. So this denominator goes to 0. It's the UV end of the geometry. So there's a boundary at the UV end of the geometry, and it's a boundary in the sense, even though it's at u goes to infinity, so it looks like it's far away. It's a boundary in the sense that massless particles, light rays, or gravity waves, reach it in a finite time. And so in order to specify what happens as we evolve in time, and here's a picture of Enter de Sitter space. This direction is time. This direction is some spatial direction. I guess it's the u direction. In order to specify what happens as we evolve the system in time, we need to specify boundary conditions at this boundary of Enter de Sitter space. And notice that this is very different from other homogeneous spacetimes with which you may be familiar. So here's a picture of Minkowski space, where the analogous thing is this light-like boundary, this scry plus and scry minus business. Or even worse, de Sitter space, which is the analog with constant positive curvature, where I guess I should have said somewhere that Enter de Sitter space has constant negative curvature. Where in de Sitter space, instead, there's a boundary which is in the future and in the past. And so these three situations of gravity living in spacetimes with different asymptotics are really very different in that the data that you need to specify the problem is very different in each case. And in the particular case of Enter de Sitter space and things like it, the thing you have to specify is data near this boundary. One piece of this data is the very fact that the geometry is asymptotically Enter de Sitter. Okay, so this statement that the geometry approaches Enter de Sitter space is a boundary condition. It's something that's just fixed, and that part of the metric, the behavior of the metric near that boundary doesn't fluctuate, and so that is a well-posed thing. Okay, and so the statement that is true will be something like some conformal field theory in d space-time dimensions is the same as gravity on some asymptotically Enter de Sitter space, where we sum over the things that the metric does on the inside. Okay, and so our job is to understand this equal sign.
So the theory now is that the beta function is because now you can perform it in infrared, right?
Right. So roughly, I just mean yes, a fixed point. Yeah. So beta equals 0. But I say conformal also because, like I said, Enter de Sitter space has, in addition to the scale invariance, also conformal symmetry.
Yeah.
So it's,
but if you deform the ADS space in the infrared,
if we deform it, then that's breaking that scale invariance.
asymptotic ADS doesn't mean anything ADS as well.
That's right. Okay. Yeah. So this will become clearer in just a moment. So a word of terminology. I'm going to refer to the gravity side of this equality as the bulk, and the field theory side as the boundary, in a way which I hope is natural based on what I just said. And here's a preview of entries in this dictionary. Fields in this Enter de Sitter space will correspond to operators in the field theory in a one-to-one way. An important thing to notice is that operators in the conformal field theory don't make particles. Rather, they make some kind of lumps of excitation, which have some power law correlations. On the other hand, fields, weakly coupled fields in de Sitter space do make particles, or at least if in the regime where you think they do. And the mass of the fields in de Sitter space will correspond to the scaling dimension of the operators, where scaling dimension is like I said, how they evolve under the normalization group. And by this equation for spinless fields, for spinless boson fields, where this is the number of space-time dimensions. And so you see the mass in units of the ADS radius is what determines the dimension. And so from just this information, you can see a useful specification that we might want to think about, which is a simple gravity theory, like, say, just general relativity, or just general relativity plus maybe some gauge field or something. So with a small number of light fields that whose dynamics we should include, corresponds to what, from some points of view, is kind of a funny thing. It corresponds to a conformal field theory with a small number of operators with small scaling dimension. So something like a rational CFT. So a rational CFT is one where there's just a small number of operators altogether. The fact that we can ignore heavy fields here means that it's okay if there's operators with enormous dimensions, that we can ignore that. Okay, this is a slide that I think everybody knows. A useful thing to compute, even if we're thinking about some Euclidean field theory, is vacuum correlation functions of local operators. And a useful way to package those is in a jittering function, where we add to the Lagrangian of the field theory some sum over operators weighted by some sources. And then if we were arbitrarily powerful, we would all like to be able to compute this, expectation value of this thing in the presence of the sources. And so then to compute these correlation functions, we just differentiate with respect to these sources. Something to notice is that this perturbation we're making of the action of the field theory is a short distance perturbation, in the sense that we're adding, we could make these sources delta functions in space, for example. So we're only perturbing the theory at a single point. And so obviously that's a very short distance perturbation. And so you're maybe not too surprised when I tell you that the way to encode this information is by changing the boundary conditions in the field theory. Because remember, the boundary of the de Sitter space is at the UV end of the geometry. And so here's the basic equation which makes this business quantitative, which is that this partition function for the field theory, including these sources, is just equal to the quantum gravity partition function. That's all. Evaluated in a situation where we specified certain boundary conditions at the UV boundary, which corresponds to the information in these sources. Now, I don't know about you, but I don't know what quantum gravity is in general. And so the case where I do know what this is when I can evaluate it by saddle point. When I can do the gravity path integral by saddle point, by solving the classical equations of motion and plugging them back into the action. And so to compute this thing, we're instructed to compute e to the minus the on-shell action, the action of the gravity theory evaluated on a solution, which is a solution of the equations of motion of this bulk action, subject to boundary conditions at this UV end, where this source, that I was calling J, is roughly the boundary value of the field of the corresponding field. Okay, and so something you should have asked me already is, well, what should we use for the gravity action? I guess you kind of asked me this already. One property that we'd like that action to have is, well, if we want it to describe the dual of a conformal field theory, we'd like de Sitter space to be a solution. And so, okay, de Sitter space has constant negative curvature, and so one way to find a solution is to study an action which is the Einstein-Hilbert term plus a cosmological constant, and then plus a bunch of other stuff that you could imagine adding, which depends on higher powers of the curvature, which you should think of. I guess I should have written the cosmological constant first, and then the Einstein-Hilbert term, and then less and less relevant terms. And okay, and so if you compute the curvature of de Sitter space, you find that it's a solution of the equations of motion of this system, so Einstein's equations with a negative cosmological constant, with this particular value of the cosmological constant in terms of the number of dimensions and the ADS radius. And notice that if we want our anti-de Sitter space to be big in units of the Planck length, which we definitely want if we want to be able to describe it using classical equations, we need to tune this ADS radius. So we need to tune this cosmological, so that is, we want L to be big compared to G Newton, and that means we need to tune the cosmological constant to be small. So this is a familiar situation from thinking about gravity in our world, and it's the same kind of idea that we're, well, I guess in the case of gravity in our world, we have an experimental reason to want to have small cosmological constant. Here, the reason is just that we want to be able to know what's going on. Okay. And so this kind of action is in fact what comes from string theory, in the few examples where we can actually tell what's going on. When we consider low energy excitations, and when we think about large radius solutions, where in situations where this ADS radius, the ADS curvature is small in units compared to the natural scale of string theory, the tension. Okay, and so a sort of demeaning statement about the role of string theory is to say that its role is to fill in the dots, is to tell us what particular combination of irrelevant terms we should put there to get a consistent theory of quantum gravity. It's not exactly fair, but that is one of the roles of string theory. Okay. So notice, or I guess not notice. I claim that this tuning, this demanding large ADS radius, is dual to putting the field theory at strong coupling. One way that you can see that this might be true, one reason to like this statement, is that it explains why you haven't noticed this when studying weakly coupled field theory, why you haven't noticed that you're secretly studying some theory living in extra dimensions. So because you won't see this extra dimension, you won't see this field theory in this gravity theory in extra dimensions in perturbation theory. At least nobody did, let's say that, though I guess many people are trying to now. And so this is a special case of a useful principle. I guess it's supposed to be called conservation of difficulty, which is that different weakly coupled descriptions of something, where I guess the keyword is different, have non-overlapping regimes of validity. And so it means that this statement is kind of hard to check. It's hard for you to prove me wrong, because who knows what a strongly coupled field theory can do. But once you believe it, then it's kind of nice, because you can learn about both sides from the other one. And in fact, this is by far our best definition of string theory, at least in asymptotically ADS solutions. Yes.
Did you mention that? So if you look at a weakly coupling quantum field theory, that can give us a definition of string theory in full power, or that was something?
That's what I mean here.
Yeah.
Not necessarily weakly coupled, because even if
we
we don't know
we know the field theory.
Right. Even if we don't know what the field theory does a priori, we know what a field theory is. At least if it doesn't have chiral matter.
Since we have a good knowledge of weakly coupled quantum field theory, why doesn't that shed light on full string theory?
Well, I think it should. You could ask, has it? And then the answer is a sociological one, probably why it hasn't shed more light. But no, I think you're right, and I think the spirit of your question is an important one in that, I think probably we can all agree that the more mysterious of the two things involved in this equality is quantum gravity, and that we kind of know what quantum mechanics is, and we should, and so once we believe this kind of statement, we should use the duality and that information to learn about string theory and quantum gravity. But that's a challenge, which I mean it's been met in some examples, but I think it's. Please go ahead. Yeah. Okay. So now I want to do a calculation to check that that I haven't been lying to you, which is to count the degrees of freedom on both sides of this correspondence. So I said to you that this holographic principle says that the maximum entropy that you can fit in some region of space in a theory of gravity is the area of the boundary of that region in Planck units with a 4. Let's forget about the 4. The 4 is not our business today. And let's check whether that can be the same as the number of degrees of freedom of the dual quantum field theory. And the answer is yes, because both of these things are infinity in the case that we're thinking about. To do better than that, we need to regulate 2 different divergences. So one of them is, so I guess let's think about it from the field theory point of view first. So we're thinking about a conformal field theory on flat space, so infinite flat space, the spatial sections of this Minkowski space. And so this maximum entropy of the field theory is infinite for 2 reasons. One is that one is an infrared divergence, that the space goes on forever, right? So there's a divergence proportional to the size of the space. We can cut it off by putting the system in a box. And then there's also a divergence from the fact that between any 2 points, there's infinitely many points because we have a continuum field theory. And so we need to cut it off with some short distance divergence. So cut off this UV divergence with something I'll call epsilon, which is, think of it like a lattice spacing. And so with these cutoffs, the maximum entropy, that is the number of degrees of freedom, is the number of sites of this lattice, which is r over epsilon to the number of dimensions, roughly. I'm thinking about a cubical lattice. Times the number of degrees of freedom at each site. So imagine, I'm going to define this symbol, which is capital red n squared, and at each one of these sites, there's n squared degrees of freedom. Think of it as, in the case of a spin system, that number is 2. No, that number is 1 in that case. Think of it as the number of spins. Okay, and so now let's do the counting into de Sitter space. So in counting degrees of freedom, we have to think about the system at fixed time, right? Think about a fixed time slice to construct the Hilbert space. And so the metric on ADS of with dt equals 0 is this. And let's think about what we mean by the area of the boundary. Again, the area of the boundary, so this is, we're trying to figure out what goes here. The area of the boundary is infinite for 2 reasons. The dual of the 2 reasons that I was mentioning. One is that these x directions go on forever. So let's put those in a box. So let's say each x goes from 0 to r. And then the other reason it diverges is because of this z integral. So here I'm just, this is a formula for the area of this metric. I need to put the square root of g because it's curved space. Evaluating the square root of g using this metric gives me L over z to the d minus 1. Square root of g, by the way, means square root of the determinant of this matrix. And this integral over z, sorry, there's no integral over z. We're integrating over fixed z and fixed t. This function of z here diverges when we take z to the boundary. Z goes to 0 is where the boundary is. And so that's a second reason that this integral diverges. And let's cut that off. Cut off that divergence by saying that, well, let's put, rather than going all the way to z equals 0, let's put a cutoff boundary at some value, which is cut off, z equals epsilon. And so evaluating this at z equals epsilon and putting the x coordinates in a box gives this formula. And so the holographic principle says that the maximum entropy should be this area over g Newton times the 4, which we don't worry about it, and equating this with the field theory divergence. Notice that so the field theory answer was this. We're comparing that to this. So the dependence on the infrared cutoff is the same. That's a good sign. If we take a bigger box on the 2 sides, we get the same answer. We get the same dependence. The dependence on our nominal UV cutoffs is the same, though we should be careful about comparing this precisely, but it's suggestive that we should think of cutting off the boundary at a finite radial coordinate as UV cutoff. And then finally, equating the coefficients, this should be a twiddle, tells us that this number of degrees of freedom per point in the field theory is equal to the ADS radius in Planck units, the ADS radius to the appropriate power in Planck units. And so that is to say that the gravity theory is classical, meaning that the ADS radius is much bigger than the Planck length, when the field theory has lots of degrees of freedom per point. So when this capital red n squared is much bigger than 1. So that's, this is a sobering lesson, but it's the fact of the matter, which, yeah. So this is it's a slightly funny, it's a very funny situation to be in, where at each point in space, there are many spins, not just one spin. So that's an essential feature of the classical limit of this correspondence. And in this limit, so n squared much bigger than 1 means that this, using this formula that we stated for the partition function of the field theory in the presence of sources, we can evaluate this on using a saddle point, in which case we get an answer which is something like e to the minus n squared. That is, the action has a factor of this in front of it, and so the largeness of this n is what controls the sharpness of the saddle point. Okay. Okay, so I'm going to spend a minute saying things that I'm not going to explain in an effort to intimidate you into believing this. So why do we believe these statements enough to try to, to use it to do physics? And I think it's important for me to admit that the main reason for that is all of the hard work that people have done in checking consequences of this duality in cases with extra structure, in particular in cases where there's supersymmetry and in cases where there's a string theory construction of the precise theory on both sides. And okay, and so so these are examples where you may not care about the specific field theory, but where we know quite a bit about it and can bring to bear various techniques that have been developed for computing, for example, things that are independent of the coupling, which go by this name, and which therefore we can compute independently at strong coupling and at weak coupling and compare them, and we know they should be the same, and they're complicated enough that there's no way they could be the same without some magic. And I guess even more impressively, the use of techniques of integrability to compute things which are a function of the coupling, where at one end, at weak coupling, it approaches the perturbative answer, and at the other end, it approaches the string theory answer, and gives an answer in between. So these things are very impressive and convincing. I think maybe nearly as convincing is the fact that this machinery pretty much always gives a sensible answer to any sensible physics question you ask it. So in particular, this has led to rediscoveries of lots of known interesting physical phenomena, which you could have imagined we would have discovered this way if we hadn't known about them already, like confinement of gauge theory, chiral symmetry breaking, thermodynamics, hydrodynamics, and a long list of things. Okay, and then third is the experimental evidence for it, which I'm not entirely kidding. This technology, as some of you know very well, has been used quite profitably in a dialogue with experiments in heavy ion collisions, in thinking about in particular the viscosity of this plasma that's formed that way. So okay, so that's the reason to like it.
Can I ask a question?
Yeah.
It didn't offer anything new in part 2.
You say I didn't offer anything new?
No, ADS-CFT didn't offer anything new. You might have thought it could have done, should have done.
Is that true? I guess there are some examples of things which historically were discovered first holographically, but which were subsequently rederived in other ways, like
triangle anomalies in relativistic.
Right. So like anomalies in hydrodynamics and Sabir's calculation with this transport in 2+1 dimensional critical points. Maybe there's some. Let's see. But there may be some new things that we just don't believe because nobody's been able to reproduce it using perturbation theory. I don't know. This is a good exercise.
No broad new phenomenon.
Say again?
No broad new phenomenon.
Broad new phenomena.
Details.
No broad new phenomena that have also been observed. I guess, certainly. Yeah. Yeah, this is a good exercise. Try to come up with something to add to this list, which we didn't know about already. And then write a paper about it. Okay. So here's an example of, so I guess this is part of this list, of a way in which, I guess it's an illustration of this statement, that the gravity description, when it's available, really tells you everything you'd want to know. It says, what are the right variables to use, and the right variables to use are the gravity variables. That's circular. But it answers these questions in terms of geometry. And so here's one of them. So I've already told you that you should think of the bulk geometry as like a spectrograph, in that it divides up the information in the theory by energy scale. In the special case of a conformal field theory, this is a very boring picture, in the sense that each slice of the thing is the same as every other one, just related by a rescaling. And in particular, this is a more general solution describing a Lorentz invariant state. It's more general in that what in ADS was just L over Z squared, I've replaced by some more general function of Z, which is where W is for warp factor. And in ADS, this just has this very simple form which goes on forever. But you could imagine other solutions where it has some more general behavior. And you should think of this time and this space as the field theory time and space variables. And the relationship between, for example, the size of an object in the field theory and the size and the proper size of some, say, ball that you put at some radius in a de Sitter space. So here's 3 balls at different values of the radial coordinate. This corresponds to objects. These correspond to objects in the field theory at different sizes because of this warp factor. So you see, things closer to the boundary correspond to smaller, have a smaller region of influence, and and there's a similar relation for the energies. And so, based on this, you can see that if we find a ground state with an energy gap, rather than, so in contrast with the case of the CFT, where there are gapless excitations, the thing that has to happen is that the geometry has to end in such a way that this warp factor has a minimum, because you see the energy of an excitation in the field theory is related to the energy of the proper energy of an excitation of the bulk times its warp factor. And so if the warp factor goes all the way to 0, find it, an arbitrary excitation in the bulk can be turned into a 0 energy excitation in the field theory. And so to get a description of a system with a gap, we need to somehow excise this infrared region of the geometry, and solutions like that exist, and they describe confined and gauge theories. And so this is a picture describing confinement of color, which is rather a difficult thing to describe in other ways. Okay, so I am not going to explain this. So this is an appendix about a way to construct field theories where the factors of n, this big red n squared that I wrote, end up in the right place. I'm sure some of you know it well, but I'm gonna skip that discussion. You can and refer you to the notes. And maybe we have time to start on the second part. Are there any questions?
I have a question in a very early slide. The black holes have the highest entropy, so there was this argument that you said that you could throw in. But then there's also this thing of phase transitions where you have both thermal ADS and this, and one of this goes thermal ADS and black holes, and the entropy of one is greater than the other depending on temperature.
The free energy of one is bigger than the other. Yes,
Yes.
that's right.
So I mean, is it contradictory? Or?
The answer is no, it's not contradictory. So the question was, so I made some assertion about that, you know, if I hand you some volume of space and ask you to construct the most entropic configuration in that region, that the answer will be a black hole. And whether that's in conflict with some things that I guess I'm not actually going to talk about that particular transition, but whether that's in conflict with the thermodynamics of black holes in empty de Sitter space. And the answer is no, and I guess the basic reason that there's no contradiction is that the boundary conditions are different. So black holes in empty de Sitter space are very different than black holes in flat space. In particular, they have positive specific heat and things like this. So okay, so it's true that the argument about the black hole being the most entropic thing didn't rely on that. If you start asking me more, sorry, one second. If you start asking me more questions about exactly what I mean by giving you a region of space and telling you to do something with it, we're going to get in trouble. So this is one place where this discussion is quite heuristic, because you know, I certainly don't mean that we're like quantizing gravity in a box of finite volume, because that's not a good idea. Or well, I don't know how to do it, I guess is what I mean. And so you probably what I should mean is we have some flat space, and then we're just yeah, okay. It's gonna be hard to pin down what I mean by the boundary. But no, there's no contradiction, I guess. Yeah. Yes, please.
Yes, just to say something else on that point. It's not exactly true that given a volume, black holes have the most entropy, because Hawking radiation happens because there's more entropy in the radiation. So there's something else. I don't know exactly what the right statement is, but there are some conditions where the black hole has more entropy, but you put a black hole in empty space and or a big box is going to keep radiating because there's more entropy in the gas.
In the infinite time, you would have a black hole in thermodynamic limits of an environment, and then that's related to the question if black hole has a temperature. If it's thermodynamic limit, it must be of the same temperature environment because it's radiating and Hawking radiation.
Right. So this is one way in which the boundary conditions make a big difference. So right. So the thing that you would naturally try to do is put the black hole in a box so that when it radiates Hawking radiation, the radiation stays there and it comes to equilibrium with its Hawking radiation. And this is kind of a tricky thing to do. And in fact, the way to do it is to put the black hole in ADS, which it's a covariant box. Yeah. So this question of exactly how to make precise what we mean by thinking about a finite region of a gravitational system is a difficult one. And in fact, the best way to do it is by going to empty de Sitter space. So let's do that. It's actually quite difficult to make this arguments precise. This arguments for the holographic principle. Okay, so
we just
how are we doing that?
Open the floor to 5 or 10 minutes of questions.
Well, I'm happy to answer more questions if people have them.
We've been going for an hour and a half.
Oh, did we start a little?
Yeah, we started a bit early.
Okay, all right. I don't want to torture people for longer than I'm allowed to. So I'm happy to take more questions, and we're right on time then, because the next thing is, the next thing is thermodynamics. I think. No, okay. So thermodynamics is soon.
So questions. I've just stopped him from going on. Someone has to ask.
Yes.
Are there papers relating the energy cutoff in the QFT to the scale cutoff in the model?
Yes. So the question is about the relationship between the cutoff on the radial coordinate and the cutoff in the field theory. So the relation that we derived here by equating the number of degrees of freedom is certainly only up to factors, and not precise. It's actually very hard to make it more precise. In particular, if you ask me, so suppose we consider an example where we know exactly what field theory is involved, like n equals 4 super Mills, where we can do a calculation on one side and do it on the other side. If you ask me precisely what regulator procedure do I have to do in the field theory to mimic the finite radial cutoff in the bulk, I don't think the answer is known. Well, I guess, okay. People have tried to make more precise this notion of RG flow, where the RG coordinate is this radial cutoff, meaning, so try to, in this classical limit, as I'm sure you know, think about relating the description that you get by fixing boundary conditions at some radial cutoff and the one where you evolve the system in the radial direction by maybe some Hamilton-Jacobi kind of thing to some other radial cutoff. And so this gives you a relationship between the fields at this value, which you think of boundary conditions here, and the fields at this value, which you think of boundary conditions at the next scale, and which, according to what I've said, is a relationship between the coupling constants at this scale and the coupling constants at this scale. And so this sort of Wilsonian holographic RG has received some attention recently. But this is purely from the gravity side, right? So not, and so I think okay, and so it's an open question, exactly what the relation is, but whether it's a good question, I'm not sure, in the sense that there's a lot of mediation between the two things, right? In the sense that the information about exactly what cutoff you're using is being filtered through also, some choice of RG scheme in both cases, which, on the gravity side, this gravity theory is making this choice for you, right? And I guess you're also choosing some coordinates as part of that information. And on the field theory side, any calculation you do, you have to define some normalization prescription. And so there's even an extra layer of ambiguity there. So the answer is I don't know exactly what the relation is. And there are a few papers who have tried to make it more precise in calculations of Wilson loops, I think. But yeah, that's the status of my understanding. Yes, please.
What is the kind of quantity that you could compute in applying holography going from the field theory to the gravity side? Like, what are the sort of quantities you could compute in the field theory and infer in the gravity side?
Well, so the statement I'm trying to sell is that they're just equal, right? So any observable you can imagine constructing in the field theory, right? So,
but if I imagine something as concrete as conductivity or superconductivity that we have done in one direction, what would be the kind of analog that you could actually compute going the other direction? I mean,
we're not very good at computing things in field theory. Yeah, I don't know.
No, it's something interesting that we have not done in the bulk side by itself.
Well, I think there's certainly lots of things that we have not done on the bulk side. So, for example, there's, in any field theory, there's a whole class of observables that you could imagine constructing by choosing some locus of space and specifying some boundary conditions there, right? So, like generalizations of disorder operators, where in this way you construct an operator which has support on some region that you get to pick. I guess a familiar example of this is a 't loops. But there's clearly a huge class of operators that you can imagine constructing there in this kind of way, which I guess in general we don't know how to compute at all, but which should translate into some gravity description, which I don't know what it is, which may be quite instructive. But I think anything that you can imagine computing, you can try to translate. That's yeah.
You said that the field theory should have a few low-lying operators with low dimensions.
In order for the gravity theory to have just a few fields with
okay,
small.
You have examples like some idea what kind of constraint is placed on the field theory?
Okay, good. So this gives me an opportunity to to emphasize the point, which is, so people, when they talk about field theory, like to construct field theories by starting with some like fields and like writing a Lagrangian for those fields. This is a really strange affectation, I think. So especially if the thing that you're after is a conformal field theory, the thing that you really need to do to specify a conformal field theory is to specify a list of operators of definite scaling dimension and their operator products and their 3-point functions. So that information, modulo maybe some global information about what happens if you put the theory on some complicated hydrogenous surface or something, completely specifies everything that you would ever want to know about the theory. And so this
It's
list,
in 1 + 1. I mean, we don't quite know it.
you're worried that there could be some like non-local observables that
Well, just knowing the OPE coefficient may not specify everything about CFTs in higher dimensions.
well, at least all the local information. Right. I mean, there may be some analogs of like the torus partition function or some, which may not, or entanglement entropy maybe you can't get. Yeah, so for that I agree it's useful to have an action. But so okay, so anyway, this is exactly the information that's in front of your face when you have the gravity description, right? There's some list of fields with their masses, and you can go to town. And so from that point of view, my answer to your question is, well, you want to have just a few low-lying operators. But I suspect what you're really asking me is, what does this mean for some Lagrangian description of the field theory? And I don't know the answer to that at all. Now, there are some, and I guess, yeah. So there are some supersymmetric field theories where this actually happens, or some version of this actually happens. Not quite as extreme as the only thing in the world is gravity, but certainly it seems to happen that at strong coupling in these theories, there are many fewer low-lying operators than you would have predicted. That for some reason, the effect of strong coupling is to make the dimensions of many operators parametrically large. And this is in contrast with what you might expect from if you just took some random, well, okay, I don't know. But in particular, all of the things that you should think of as excitations of strings, so big floppy string excitations, are just a very high dimension, and I guess that's a direct result of having a large ADS radius in units of the string length. And exactly why that happens, I think, is a total mystery. And what the ingredients are that are necessary to make that happen, I think, is a total mystery. Yes, please.
Does ADS-CFT provide a way for tabletop experiments to probe Planck scale physics?
Yeah, maybe. That would be really cool. Certainly in principle, a thing that you should not go and do is, design some optical lattice in which you can put cold atoms, which simulates some lattice description of n=4 super-ring Mills. This is something there's no obstruction to doing this, I don't think, except for a lot of practical considerations. So there's a knob on your experiment which is n, and one which is lambda, and So in principle, yeah. Exactly. But I think a more interesting question about that is what you should measure, and I guess this is what Raghu was asking. What you should measure to learn something about that quantum gravity theory. And yeah, I don't know. This is a good question. Do I have a good answer? I don't know a good answer off the top of my head. Yes, please.
If I have some UV theory and I perturb by some relevant operator, does the holographic RG flow help us decide which CFT that it flows to?
Yeah, so this is a big industry. So if you have a UV fixed point with a gravity dual, then that gravity dual comes with some list of fields, some of which will correspond to relevant deformations. And so like I said, perturbing the theory corresponds to some perturbation of the boundary conditions at the UV end, and that gives you some sort of boundary value problem, where you want to construct a solution of this gravity system with the field, with some given boundary conditions, and and it's a little bit tricky because you don't know what it does at this end, right? The question you want to answer is, where does the field evolve to, and where does all the other stuff evolve to? But certainly there's a big industry of the construction of such solutions, and many examples exist of both flows between fixed points and flows to states with mass gap. So yes. On the other hand, there are certainly also cases where we don't know what the endpoint of the perturbation is. For example, because it leads to a flow outside the gravity regime. That's an annoying possibility, which is always there. Okay, maybe we pause. Yeah, lunchtime.
Questions?
Okay.
About this Hamiltonian as a function of u that we discussed. So this was written as a field theory in the sense that it was a Newton. So this is an infrared limit of your lattice spacing.
Right.
So this has to be understood as an effective field theory for u much less than the lattice spacing.
That's a good idea. Yes.
So I guess presented in this way, the best thing one can hope is to describe the infrared dynamics with the ADS-50 or.
Well, certainly the easiest thing to.
Because the field theory emerges in the infrared.
Yeah, the easiest thing to describe with our current understanding is continuum theories. Yeah. Whether we can say something about lattice theories is maybe. Yeah, it's not no.
Okay, let's wrap up and thank John for a very nice introduction.